Welcome to this lecture. This is the first lecture of week 8. In the previous 2 weeks, we have discussed about the concept of weak convergence for random variables, and in the last week we have specifically pointed out that there is a very special example of weak convergence, which essentially comes from the motivation of looking at the rate of convergence type results for the law of large numbers. And these results that we had discussed already, we decided to call it the central limit theorem. In the previous week, we have seen a simple version which we have called as the Lindeberg-Levy central limit theorem or the classical central limit theorem. But in this lecture, we are going to continue to look at results of that type, but under more general conditions. So, without further delay, let us continue the discussion using the lecture notes. So, as pointed out, we are going to discuss about the generalizations of the central limit theorem that we have already seen, which was the Lindeberg-Levy central limit theorem, also the classical central limit theorem. So, now in these generalizations, we are going to drop the condition of identical distributions of the random variables in question. So, here note that in the classical central limit theorem, we have assumed the random variables to be independent and identically distributed. So, if we drop the assumption of identical distribution, we are going to continue with the assumption of independence. So, the sequence of random variables that we are going to consider, they will be assumed to be independent. Now, we clarify the setup that we are going to talk about through the following definition. Now, we are going to look at certain special collection of random variables, which we are going to call as the triangular array of random variables. So, the idea is this, that for each natural number n, suppose I consider a collection of random variables denoted by x n 1, x n 2 up to x n r n. So, here r n is some natural number again, but depending on n. So, now here the assumption will be that this collection for each fixed value of n should be independent random variables, and these random variables may be defined on these kind of probability spaces. So, for each fixed n, the collection of random variables that we consider is defined on these omega n f n p n, may be depending on n, and we want these random variables to be independent. And then given such collections for each n, look at now the whole collection of random variables. Now, note that these random variables may not be defined on the same probability space. So, we are now looking at all these random variables, and this we are going to call as a triangular array of random variables. Alright. So, with this setting, we are now going to focus on certain structural properties of such triangular arrays. Now, while considering such triangular arrays, as stated earlier, we might not be able to talk about the independence of, let us say, x n j and x m k. So, here if my n and m, the natural numbers are distinct, then the random variables that we have come from different collections and may be defined on different probability spaces. So, in general, we might not be able to talk about the independence of these two random variables when n is not equal to m. However, the structure of triangular arrays that we are going to focus on can be visualized like this, that for n equals to 1, I am given some natural number r 1. So, therefore, I am having these many random variables. Suppose I write them in the first row. Then for n equal to 2, I will have another natural number, call it r 2, and then I will have that many random variables on the second level for n equal to 2. So, here note that for n equal to 1, we might be having some probability space omega 1 f 1 p 1, where all the random variables on the first row are defined. For n equal to 2, I will be having possibly different probability space, where the random variables from the second row may be defined, and so on. If we continue this way, we are having the whole collection that we are focusing on, and this is what we are going to call as a triangular array. Now, the idea is if we visualize a triangular array in this way, then row wise the random variables that we see are independent. Now, we are going to focus on additional structural properties, but to reduce our notational complexity, what we do is that in all the expressions that we use, we are going to write this symbol to denote the underlying probability measure. So, here from time to time as n varies, n is denoting the number of the row, there we should have the probability measure P n, but we simply drop the subscript n. We understand that which probability measure we are using, but just for our notational simplicity we write P and drop the symbol n, and the corresponding expectations we will also write using this symbol. We will suppress the symbol small n, but again the understanding will be that the corresponding random variables that we are considering, the laws are considered with this probability measure and the expectations are considered with respect to that appropriate probability measure on the level n or the row n. Now, with this notations in mind, we now go on and set up some further notations for our subsequent results. So, now the idea is that given any such triangular array, we are going to look at something called the row sums. So, fix any n, a positive integer, look at S n. What we are doing is that we are just adding up the random variables that are available on the nth row, and if I add them up I am going to get S n, that is the row sum. And what we are going to do is that we are going to assume that these random variables in question have finite variances. So, this is in the setting of the Lindeberg-Levy type results that we have already seen. We are simply going to continue assuming similar conditions. So, here we are now assuming that S n's having finite variances, but now let us write the variance of S n as small s n squared. So, small s n itself is the standard deviation of the random variable capital S n. So, now since the capital S n is made up of the addition of these random variables which are independent, the variance of capital S n is nothing but the variance of x n j's summed over j from 1 to R n. But now let us write using sigma n j squared the corresponding variances of these random variables x n j's. So, therefore, we have an expression for small s n squared in terms of the sum of the variances, and the main assumption that we are imposing is that the small s n squared and therefore, the sigma n j squared, all of these quantities are finite. Furthermore, we are also going to assume a non-degeneracy condition that the small s n squared is positive. So, that simply is telling us that the capital S n random variable is non-degenerate. So, just to clarify, in the setting of Lindeberg-Levy central limit theorem, we have pointed out in note 15 of week 7 that if we work with degenerate random variables, that is the case when the variance is 0, then there is not much point of interest because all the underlying random variables are degenerate. So, we do not go into the degeneracy type results when we are considering more general setting as we are discussing now. Now, another notation we are going to use is the notation for the expectation of these random variables, and we are going to write mu n j's for the same. So, now let us set up the main condition that we are going to discuss. So, here we are going to call this the Lindeberg condition. So, the idea is that you consider a triangular array as stated earlier. We are going to say that this array satisfies the Lindeberg condition if for all epsilon positive I am going to consider certain truncated second moments. So, the idea is fix any j from 1 to R n, then look at the x n j, that random variable, subtract out the fluctuations from the mean. Now, here if that quantity is greater or equals to epsilon times the standard deviation of capital S n, then on such set you look at the second moment of the random variable x n j. So, here we are always going to talk about the central second moments. So, here what we are doing is that we are looking at this truncated central second moments and then summing them up. Finally, we will rescale them through the variance of capital Sn, and if it so happens that as n goes to infinity, this quantity goes to 0, we are going to say that the Lindeberg condition holds, and we want this to hold for all positive epsilon. Now, this is the application of this condition, that immediately we are going to have a central limit theorem by using this Lindeberg condition. But now, the proof of this kind of a central limit theorem, this more generalized version, again goes through the pointwise convergence of the characteristic function that we have talked about in the Lindeberg-Levy central limit theorem. So, here we are simply appealing to the Levy's continuity theorem and saying that the corresponding characteristic functions converge pointwise. So, let us state the Lindeberg form of the central limit theorem, and we do not discuss the proof. Alright. So, the idea is that you start with a triangular array of such random variables. Remember, we are always considering that at the level n, all the random variables that we consider are independent of each other. Now, suppose this triangular array is satisfying this Lindeberg's condition, then it says that look at the row sums, but consider the normalized version, meaning you subtract out the mean and then divide by the standard deviation. Now, this centered and scaled, the normalized random variables will now converge in distribution to z, which is having normal 0 1 as its distribution as n goes to infinity. So, this is the extension of the Lindeberg-Levy central limit theorem, the simple version that we have seen earlier. We still continue with the assumption of independence, but we have now dropped the condition on the identical distribution part. So, here we are allowing the random variables to have different possible distributions, but then we are again considering similar summations and we are looking at the centered and scaled versions of them and claiming the convergence to standard normal random variables as n goes to infinity in the sense of weak convergence. So, that is the Lindeberg form of the central limit theorem. Alright. So, now we are going to focus on certain special cases of this Lindeberg's central limit theorem. So, the first case is that we go back to the Lindeberg-Levy central limit theorem, the classical central limit theorem we have already seen. So, suppose you consider a sequence of IID random variables. So, our assumption here again is that the variance of x 1 is positive, call it sigma squared. So, this is the common variance of all these random variables. Now, also write by mu the common mean of these random variables. Now, look at this sequence of random variables as a form of triangular array. Now, here you note that all the random variables now are getting defined on the same probability space. So, this is a special case of the triangular array that we have defined earlier. What we are doing is that at the level n being 1, we are considering the first random variable, then at the level n equal to 2, we are considering the first two random variables and so on. So, likewise, we are going to look at all the random variables as n increases and we are going to have a triangular array. Now, here what happens to the variance? So, here what is happening is that the variance of the row sums we have denoted as small s n squared, that is made up of the addition of the individual variances of these random variables x 1 up to x n. But since all the variances are same, you are just going to have n times sigma squared as the value of the small s n squared. Now, since the random variables x n's are assumed to be identically distributed, let us now try to check that the Lindeberg condition holds. So, what we are saying is that let us work with some epsilon positive. Look at now the truncated second moments, the truncated second central moments that we are looking at. So, here we are focusing on such events and on such events we are looking at these central moments. So, here if you add the terms and rescale by s n squared, then we simplify this expression. Let us see what happens. So, first we plug in the expression for the small s n squared, and then we also put in the term here inside the range of integration. But now note that in this integration that we are looking at, all the random variables x j's that we are looking at, all of them have the identical distribution, and therefore, the type of integrations that we are considering here is actually independent of j. And moreover, what is happening is that if you observe that these are independent of j, then we can simply reduce to this expression. But now as n goes to infinity, the range of integration is actually going down to the empty set, and therefore, these terms are going to 0. So, therefore, for any epsilon positive, we have shown that the corresponding terms are going to 0, and hence the Lindeberg condition is true. So, therefore, if I go back to the Lindeberg central limit theorem, then we can have that if you are working with a IID sequence of random variables with finite variances, then it is actually implying the classical central limit theorem or the Lindeberg-Levy central limit theorem. So, this is therefore a generalization of the result that we have discussed earlier. Another important form of the Lindeberg's condition will be as follows. So, suppose we are again going to consider a sequence of independent random variables, but now consider the case that they may have different distributions. However, suppose there exists some m greater than 0 such that almost surely all the random variables are bounded above by m. So, we are looking at the boundedness in the sense that mod of x n is less or equal to m. So, this should happen for all n and with full probability 1. So, this kind of condition is essentially some kind of uniform boundedness of the sequence of random variables that we are considering. We are going to see certain applications of such things later on. And moreover, we also assume this second condition that the standard deviation of the row sums given by small s n go to infinity as n goes to infinity. So, we assume these two conditions when we have a sequence of independent random variables, and our claim is that under this setting the Lindeberg condition holds. To see this, let us do certain very simple calculations using the Chebyshev's inequality. Look at this type of truncated second central moments in question. So, for any fixed j, look at the fact that the term inside the integrand here is dominated from above by 2 times m. Why? Because since mod of x j with full probability is dominated by m, immediately expected value of x j, the modulus value of that will also be dominated by m, which is nothing but our mu j. So, therefore, modulus of x j minus mu j, if you want to estimate, that is less or equal to modulus of x j plus modulus of mu j, and therefore, this is less equal to 2 times m. So, that is the simple bound we are applying here. So, therefore, the truncated second central moments that we are looking at has an upper bound given by 2 m whole squared multiplied by the probability of this event. But now, here is where we are applying the Chebyshev's inequality and bringing in the corresponding variances. But now, we are also going to add up these terms as j varies from 1 to n. So, that is what we do. As j goes from 1 to n, if we add them up, then note that summation sigma j squared from j equal to 1 to n is exactly given you small s n squared. So, if you add them up, then inside this summation is going to give you 4 m squared divided by epsilon squared, because the small s n squared has cancelled off. Now, if you further divide the terms by 1 by s n squared, that term remains here. By our assumption, s n squared goes to infinity as n goes to infinity. So, therefore, the whole expression that we are looking at for any epsilon positive goes to 0 as n goes to infinity. So, therefore, the Lindeberg condition holds. So, in the Lindeberg form, we have seen these two special cases, and in the Lindeberg form, what actually happens is that we are trying to get certain estimates on the truncated second central moments. So, this is the idea that we are following. But now, in practice, what happens that handling these truncated second central moments are usually difficult. So, in that what we do is that we look at a slightly easier condition to verify, which is also a special case of the Lindeberg's condition that we have discussed. So, let us see that condition. All right. So, this condition is typically called the Lyapunov condition. So, the idea is again you are going to look at this triangular array of these random variables, and you are going to say that this triangular array satisfies the Lyapunov's condition if for some delta positive look at the 2 plus deltath order absolute central moments. So, these are the quantities that appear here, then add them up and scale by this order of the variances of the corresponding row sums. So, here we are scaling by small s n to the power 2 plus delta. So, the focus is always with the moment of order now 2 plus delta, which by our assumption is actually strictly greater than 2. And the idea is if you can control the central moments, the absolute central moments of order 2 plus delta, then you can also control the second central moments, and that is what we observe in the next result. So, our statement says that suppose a triangular array of random variables satisfy the Lyapunov's condition, meaning that limiting statement holds for some delta positive and essentially giving us some information about the 2 plus deltath absolute central moments. So, now if that holds, then we must have the Lindeberg's condition being true. So, that is the statement. So, let us see how it goes. So, suppose the Lyapunov's condition is true for some delta. So, now while looking at the Lindeberg's condition, we need to look at certain truncated central moments of order 2. So, let us look at that. So, we start with this quantity. Now, here we write it in terms of the corresponding integration, but just observe that we really want to look at this part of the range of integration. So, that is what is required when we are looking at the corresponding Lindeberg's condition. But here what is happening is that the term inside the integrand can be thought of as x n j minus mu n j to the power 2 multiplied by the same thing to the power delta. Now, the part to the power delta is greater or equals to this quantity. So, that we bring outside our integration, and we are simply left out with these truncated second central moments that are required in the Lindeberg's condition. Now, what happens is that by the Lyapunov's condition, now observe that this quantity which appears in the Lindeberg's condition is upper bounded by this quantity, and here what we have assumed is that by the Lyapunov's condition this goes to 0, and this is true for all epsilon positive. So, in this expression epsilon appears here, and as n goes to infinity it does not play any role. So, for any arbitrary epsilon positive as n goes to infinity, this right hand side goes to 0. But now, the left hand side is non-negative, and therefore, it must also go to 0 as n goes to infinity, and hence the Lindeberg condition holds. So, consequently, if we assume the appropriate condition of order 2 plus delta, which is essentially the Lyapunov's condition, then we essentially have what is typically called the Lyapunov central limit theorem. So, this is a special case of the Lindeberg central limit theorem, and this is usually easier to verify. All right. So, now the statement goes like this, that you consider a triangular array of random variables which satisfies the Lyapunov's condition. So, Lyapunov's condition refers to that appropriate limit holds for some delta positive, which is essentially giving you some control of the central moments of order 2 plus delta. So, here we are always going to look at absolute central moments. Now, the statement says that as a consequence of the Lindeberg central limit theorem, these centered and scaled random variables which are normalized now, meaning mean 0 variance 1, they converge in the sense of weak convergence to a standard normal random variable as n goes to infinity. So, here so far what we have seen are the discussion involving the Lindeberg's condition, which is a sufficient condition to ensure the convergence to normal distributions for the row sums that we consider. So, for these row sums we are always going to look at the centered and scaled versions, the normalized versions, and the statement is saying that under this sufficient condition, which is the Lindeberg's condition, this actually implies this kind of a central limit theorem. Now, we are going to discuss a partial converse to these results. So, here this result is due to William Feller. So, here what we are considering is this, that we continue with such triangular arrays of random variables such that for all epsilon positive, this triangular array satisfies a condition that the random variables are somewhat small in size as n goes to infinity. So, more formally this is the condition that we want, that as n goes to infinity, look at these probabilities. Here we are saying that the fluctuation away from the mean in the distance of the form epsilon times the standard deviation of capital S n, that probabilities uniformly. So, that is the feature of this maximum. So, uniformly they go to 0 as n goes to infinity, and this should happen for all epsilon positive. So, this is in some sense some uniform bound or uniformly small kind of condition on this triangular array, and moreover assume that the central limit theorem type result is true, meaning that these centered and scaled random variables converge in distribution to a standard normal random variable as n goes to infinity. Then the result states that this triangular array must satisfy the Lindeberg's condition. So, under this additional condition, which is in some sense a uniform bound or uniform smallness of these random variables, they imply that the corresponding Lindeberg's condition is actually also necessary for the central limit theorem to hold. So, this is the converse due to Feller, and we do not discuss this in this course. So, we only use the understanding that we derive from this result. However, we point out that here this additional condition of uniform bound or uniform smallness that we are using, that may not be true in general. So, let us consider a sequence of independent Gaussian random variables with these very special structures, that suppose you have this sequence of random variables x 1, x 2 and so on, all of these are having mean 0, but look at these specific variances. So, what we want is that the first two random variables x 1 and x 2 have the variance 1, but then from 3 onwards all the variances are of the form 2 to the power n minus 2. So, by this specific choice, what we immediately will conclude that if we now look at the corresponding partial sums or the row sums, then they are also mean 0, because the original random variables have mean 0, and moreover the variance of capital S n, which we denote by small s n squared, is the sum of the individual variances. But now use the structure of this geometric series and we end up with 2 to the power n minus 1 as the value of the variance of capital S n. Now, here what we can immediately also check that these centered and scaled random variables are actually following the normal distribution with mean 0 and variance 1, and this is true for all n. In particular, as n goes to infinity, these centered and scaled random variables of course converge in distribution to a normal 0 1 random variable. Now, what we are now saying is that actually the additional condition that we have pointed out in the Feller's theorem fails. Why? Look at these probabilities that we want certain uniform bound about. So, here we have used the fact that the corresponding mean are 0. Now, here since the quantities that we are considering, here we are taking a maximum. So, therefore, this maximum quantity is at least this much. So, here we have just taken j equal to n case. So, let us look at the quantity involving j equal to n. So, here note that if you rescale the things, then this is actually in terms of the probability of a normal 0 half random variable y. So, which is this expression? Why is this true? Because you note x n follows the distribution normal 0 with variance 2 power n minus 2, and what we actually have is that small s n is equal to square root of 2 power n minus 1. So, therefore, if you divide capital X n by small s n, that is going to follow normal 0 with variance half. So, this you can immediately check. So, that is what we are saying, that if you plug in some random variable y which is following normal 0 with variance half, then this probability is same as this probability that mod of y exceeds epsilon. But now note that here the final expression does not depend on n, and therefore, the maximum quantity that we are observing on the left hand side has a uniform lower bound independent of n, and the uniform lower bound is actually always positive for this random variable y. So, therefore, we immediately claim that as n goes to infinity, these maximum quantities, meaning the uniformly these probabilities do not converge to 0. So, therefore, what we are saying is that the additional condition in the Fellers theorem fails. What you can now observe is that we have actually the central limit theorem type result. We have actually pointed out that at each level n, the corresponding centered and scaled random variables are actually having normal 0 1 distributions themselves. Now, you can try to check whether the Lindeberg condition holds in this specific situation. I leave you to check this. So, this is left as an exercise for you. And finally, I also give you another exercise to try out. So, this is again some form of the Lyapunov central limit theorem that we are going to use. So, sometimes this kind of conditions are also useful. So, suppose you have a sequence of independent random variables which have mean 0, but suppose that the variances of these random variables, if you consider the corresponding series, they diverge to infinity, and moreover you have a uniform upper bound for the 2 plus delta absolute moments for these random variables. So, this should hold for some delta positive. Then the claim is that look at the corresponding partial sums, scale it by small s n, then they converge in distribution to normal 0 1 random variables as n goes to infinity. So, in this lecture we have seen certain extensions of the Lindeberg-Levy central limit theorem or the classical central limit theorem, and essentially we have focused on our discussion on the Lindeberg's condition. Now, more generally we are going to see that there are other further nice results which also carries over in terms of the weak convergence. So, we have so far been concentrating on the central limit theorem, but in the upcoming lectures we are going to focus on some other nice results involving the weak convergence, and in particular we are also going to look at some further nice applications of the central limit theorem. So, that is what we are going to discuss in upcoming lectures. We stop here. Thank you.